In this video, we're going to switch gears from looking at the algebraic curves that we looked at in the previous videos, which are algebraic curves in the affine plane. We also call them affine algebraic curves, to looking at projective curves. Up to this point, we've looked at curves that we would maybe describe as being in the usual xy plane. This is also called the affine plane, and so there's a problem with looking at these types of curves. For the applications that we want for GAPA codes, we need intersections of curves to be pretty well behaved, but that's not the case with affine curves or curves in the affine plane. So in order to make these intersections more predictable, we're going to need to do something a little bit different and construct a new plane which is going to look like unlike any plane that you've seen before. And this is going to be a plane so that two lines will always intersect somewhere. So the way that we define this is by starting with points in R3, and then we decide that 2 points are equal if there's a non-zero lambda such that one is a multiple of the other. So we're taking points in R3 and then deciding that they're being kind of divided up into groups so that some of them are equal. There are a few other ways that you can think about the projective plane. You can think about this as the set of lines through the origin in R3, or as the sphere, where once you take points on the opposite side of the sphere from each other and then glue those together. So it's sort of hard to imagine doing this physically because it ends up being really twisted over itself. But like you'd take the North Pole and the South Pole and glue those together, and all of the other opposite points would have to also be glued together. For how we write points, we're going to write these as x colon y colon z, and this is notation to distinguish between projective points and affine points, because it can get really confusing if you're writing all of your points in the same way as x comma y comma z. As a note, I think the book sticks pretty consistently to just doing x comma y comma z, which I find very confusing, so watch out for that if you're reading the book. But in our class, we'll write these x colon y colon z to make sure that that distinction is clear. So once we write a point in P2 as x colon y colon z, we call these homogeneous coordinates to once again kind of distinguish them from normal coordinates in the affine plane. So when we're looking in homogeneous coordinates, this is going to mean that 1, 1, 1 is equivalent to any multiple of 1, 1, 1. So this is equivalent to 2, 2, 2, or 1, 1, or minus 1, minus 1, minus 1, or any other multiple of 1, 1, 1. When we look at 1, 2, 3, this is going to be the same as 2, 4, 6. We could also do 1/2, 1 3/2 multiplying by 1/2 there. For 1, 0, 0, this could be like 10, 0, 0, or like pi, 0, 0. So just multiplying by a scalar, you stick with the same point there. And if we look at 0, 0, 0, for constructing the projective plane, notice that we only looked at non-zero points back here. So that's going to mean that when we look at 0, 0, 0, this is not in P2, so not in projective space. So the whole idea behind constructing the projective plane is that we want to construct a space where parallel lines will eventually intersect at a point at infinity. So a way that you can kind of think about this is that, in perspective paintings for art, we'd imagine lines like through here, through here, through here, and here, as being parallel lines, but we can see that, with perspective, there's kind of this point at infinity where these lines eventually intersect. So it's roughly the same idea with projective space. This isn't a great visualization tool for projective space because like these parallel lines in this picture don't intersect, but they would have to in projective space. So there's a little bit more weird stuff going on, but this can give you a kind of idea about sort of what our aim is here. So the affine plane can be embedded in P2 by taking a point xy and mapping it to the homogeneous coordinates x, y, 1, so having the third coordinate just be 1. And then when we look at the points x, y, 0, where x and y are not both 0, these are points that are not coming from the affine plane, and these are the points at infinity that make it so that any parallel lines in projective space are going to eventually intersect. We would like to be able to talk about algebraic curves in P2, similar to what we've done in affine space, looking at zeros of polynomials. But there's an issue with this, which is that not all polynomials are going to be well defined on P2. So for example, if we look at this polynomial f of x, y, z equals x, y plus z plus 1, and we look at the point 1, minus 1, 2 in projective space, that's the exact same point as 2, minus 2, 4, but when we plug those coordinates into this polynomial, if we plug in 1, minus 1, 2, we're going to get minus 1, plus 2, plus 1, and so we get 1 out of that. But if we plug in 2, minus 2, 4, we've got minus 4, minus 2, plus 4, plus 1, so we get minus 1 out of that. So this is a problem because these are supposed to be the exact same point, so we shouldn't get different values from plugging them into a polynomial. So it turns out that we're only going to be able to look at some polynomials over projective space, and these types of polynomials are called homogeneous polynomials. So a polynomial is homogeneous if the total degree of all of its terms are the same. So by total degree, I mean that you look at the degree of all of the variables in that term and add them up. So when we're looking at x, y, this has total degree 2, y has total degree 1, z has total degree 1, and constants have total degree 0. So this is not homogeneous. For g here, when we look at this, xy has total degree 2, y squared has total degree 2, and z squared has total degree 2, so g here is homogeneous. So this polynomial is going to be well defined on P2, and so this will work for making algebraic curves in P2. For taking curves in R2 and translating those curves into projective space, we're going to have to get homogeneous polynomials out of them in order to make sure they make sense. So the trick to homogenizing polynomials is to insert powers of z in order to make the polynomials homogeneous. So looking at this polynomial, f of xy equals xy plus y plus 1. So this was a polynomial that we saw that was not homogeneous. In order to make it homogeneous, we're going to add some z's in there to make sure that all of the terms have the same total degree. So for the first one, xy, since this has the largest total degree, I'm not going to need to insert any extra z's in there. But coming to the next term where we've got y, now I want the total degree of this term to match the total degree of the previous one. So I'm going to have to insert a z in there so that now this has total degree 2. And for the constant term here, I'm going to need to put in z squared in order to make this total degree 2. So now all the terms in this polynomial f tilde have total degree 2, so this is a homogeneous polynomial. So we can do this to take affine curves or algebraic curves in kind of the normal plane and homogenize the polynomials in order to get a projective curve. So when we look at xy plus y plus 1 equals 0, our projective curve is going to be defined by xy plus yz plus z squared equals 0. And then when we look at x squared plus y squared equals 1, it might be tempting to say, oh, the polynomial's homogeneous here. We'd be fine, but that constant 1 is going to be a problem here. So this would actually turn out to be x squared plus y squared equals z squared for the projective curve there, and that's because you can think about this as being given by the polynomial x squared plus y squared minus 1 equals 0, which then you need to homogenize that polynomial on the left. And similarly for y equals x cubed plus x plus 1, we're going to need the total degree for all of these terms to be 3. So then we'd need y z squared equals x cubed plus x z squared plus z cubed, and then this gives us a nice projective curve there. So the goal of doing this is that we're going to be able to use these projective curves in order to be able to define some kind of bizarre codes, which are GAPA codes.